Okay, so good afternoon. My name is Peter Szegedi. I'm a project development officer at Terena, and I'm chairing this session and the following two sessions in a row, which is about the virtual technologies and especially about the Federica project. So we're going to have two more sessions in the afternoon dedicated directly to the results of the Federica project or talks related to the Federica project. But this session is more general. There are more general talks on the virtual technology. We have three speakers. Our first speaker is Jean-Marc Uzet, the European Technical Director of Juniper, and I think the best flamenco dancer of Juniper.
Thank you very much, Peter. So good morning, everybody. It's a real pleasure to be here today. And for those who are asking what this title means, I wanted really to make my proposal as sexy as possible. Unfortunately for me, I have so many slides, so I cannot spend too much discussion on that title. But maybe I'm going to come back to that point later. Basically, I'm going to talk about virtualization, but from the angle of how this paradigm can now be considered to be deployed in production networks, so typically a national research network, but why not a regional network or metropolitan networks up to the campus. The idea is to integrate this paradigm into existing infrastructure and see what if it could be actually the next generation or next step of development of very advanced research networks. So I'm going to, after a short introduction, to also share with you a bit the view we have regarding the applicability of virtualization in the commercial service provider. I think it's always interesting to do the parallel with what you do, because what you do is actually prefiguring in many ways what is going to be available in commercial networks. So I want to share with you that as well. And also, of course, we are going to look in more details the foundation building blocks that could be used today in your networks in order to enable these capabilities. So definitely, RNE is paving in the evolution of networking, and we have seen that many times in the last years. So just to mention a few examples with IPv6, which was deployed many years ago in your networks, is now being considered very seriously by commercial networks who are now in this transition process of moving to IPv6. Even the LightPath paradigm, which was really focusing on the specific needs in your community, is a concept that is being used by commercial networks to offload, for example, internet traffic directly from one POP to another, bypassing the routing infrastructure, so doing some kind of shortcut path in the network. And another example is the AAA, which is really something that you have developed that allows you here to connect to the network infrastructure by using the same credential that you are using in your campus. This is something that is now being considered very seriously by commercial networks to enable what they call value per bit, so developing new business model in the internet. One key application related to that is targeted advertisement, which is all about exchanging identity between different stakeholders. So again, here you have taken an advance that is going to be leveraged in commercial networks. So what's next? And next is, of course, the purpose of my talk here. So I want to explore with you if virtualization could not be the next step of service development in your community before it reached the commercial environment. So there are already some initiatives. I'm sure you all heard about them. One is Federica, which is an EC-funded project, which is actually exploring virtualization as a service because it offers to researchers the possibility to conduct some experiments in a dedicated network, but a dedicated virtual network. So there is one single physical infrastructure. On top of it, we slice the infrastructure in independent networks which may have completely different topologies. It's constituted of routers, of logical switch, of logical nodes, and you can have your own environment for testing that you entirely control, independent of the other slices that are being used by other projects. And also you can reproduce some experiments by building the same environment that you used maybe a few months ago in the first stage of your experimentation. So that's something that is being explored. It's not a research project as such, although there are some research activities related to control plane and middleware required to manage all these building blocks. But it's, before anything else, it's really a service that is being provided to the community. So the service angle is really explored in that project. Another project is Manticore, which is also a key initiative in Europe, which is actually looking after how an operator can start to share some building blocks of its infrastructure and basically the routers, how the routers of one operator or multiple operators, so we can consider multiple stakeholders, are sharing part of their routers, of course by using virtualization, so that the customer can build its own network and dedicated network he has full control in. So this project is looking specifically after the tools and middleware that can be used, the management system can be used in order for the operators to propose some routing nodes and allow the customers to build its own network and manage it. So why is this interesting also for commercial networks? And you know, all is about consolidation and convergence, which is a buzzword we have heard so many times in the industry. But the fact is that today, most operators still run multiple networks in their infrastructure. They have to build overlay networks because it's very complex to converge. I mean, for many reasons. One is organizational. The guys in the mobile don't want to share or work with the guys from the fixed network. There are also some regulation aspects. You may not do the same thing if you start to converge different networks because the regulation is strictly separating the different services. Also, there are many aspects related to technical, operational aspect or business aspect that explain why the operators today are still building several networks for different services. And three main categories are wireline, wireless, wholesale, but even in one single category, you may have multiple networks. For example, in the wireline, you may have one network dedicated for internet, another one for business services with VPN services, another one for voice, another one for residential customers. And that's the reality. It's really challenging for the operators to converge because of all this organizational aspect, regulation aspect, and sometimes even the internal rules in the company doesn't allow to mix things together. So, however, there is still a need to converge because the operators, they want to reduce, of course, the expenditure, so the CapEx and the OpEx. So the virtualization is here an opportunity for them because with virtualization, you can consolidate in one single infrastructure while at the same time keeping a strict separation between the different networks. So that's really interesting for them. So if we take this example of multiple networks that you can see with colors, the future or the evolution of commercial providers could be something that will actually benefit from the fact that in most cases, these networks, they share the same locations. In one single POP, in one city, like Madrid, for example, or Malaga, they may have multiple routers, one for each color. So you could benefit from this fact by consolidating and putting these routers, but as logical entity part of bigger and routers that leverage the virtualization technology. So the commercial operators are looking now at this new model where they would have very limited number of routers in the network, but shared by multiple networks. And that, the great thing here is you reduce the CapEx, OpEx, while keeping a strict separation between the services. So it has no impact or very few impact on organizational aspect and operational aspect. So that's the reason why there is also a driver in commercial networks. However, we are far from that model. So today, if we come back to research education networks, the NRN typically builds one big network that connects everybody with internet and actually advanced internet because it has some V6, multicast capabilities, etc. And there is a need, and in some places, in some countries, there are some parallel networks that are being built, sometimes by the NRN itself, in order to serve some specific project or communities. For example, to support grid in the country, or to support an experimental network. They may build a separate infrastructure as well. And there are other needs coming, like national project or European project with EC, with the European Commission. So the challenge here for NRNs is to allow or to ease the construction of such infrastructure in their country. And that can be translated into an opportunity for NRNs, but which is then translated to vendor mission, allowing this consolidation, instead of building separate infrastructure, being able to use one single foundation, one single infrastructure used by NRN, and be able to, with the virtualization, to build separate networks which are totally independent. From operation point of view, of course, the NRN, which has a very expert NOC, is going to manage the infrastructure, so the physical network. The NRN may also operate some of the virtual slice, like the internet network, but you may have completely separate operational entities managing the different slices. So if you have a specific project, you may have one NOC managing its slice, and for the simple reason that this is exactly the goal we want to achieve here, allowing some researchers to work on their network and dedicated network, but benefiting from the NRN providing the full infrastructure as a virtual and logical network. So let's have a look now to the requirements, and I'm going to actually share with you thoughts on 4 different topics which I believe are the key building blocks to achieve that vision. We are going to talk about scaling the data plane. We are going to talk about decoupling the control plane from the data plane, which is also a key enabler, and this way also scale the control plane. And then we are going to talk about better integration of IP and optical network, because obviously the transport layer plays a key role in the virtualization. If you virtualize, you need to have multiple links, but we want to leverage the same infrastructure. And the 4th point is, I think, also a key enabler, is the path towards programmable networks. If you build such a network, then you would like to have others or new services being deployed in specific slices. And why not thinking about creating your own service environment, creating your own applications that could be run inside the infrastructure instead of an overlay service. So let's have a look to these 4 points. First, with the data plane. There is an increasing demand for deterministic performance in the data plane, in particular with this vision. The reason being that each project or each slice, we need specific QoS requirements for different reasons. One being the reproducibility. If you do an experiment in a slide and you come back 2 weeks later, you want to have exactly the same environment. So you want to make sure that by using the virtualization technique, the NRN will be able to provide you deterministic QoS, so you will have exactly the same environment. Also, if this model is successful, there will be many virtualized slices, so which means that the network has to scale, right? Because we are going to increase the number of networks. And the physical location of a router may be actually decoupled from the virtual slice. You may have one physical router somewhere hosting many logical routers, and the researcher do not necessarily need to know where the router is physically located. However, you want to know probably the delay between the routers, because that could be a condition for the experiment, but not necessarily exactly where it is. So we may have 2 routers actually hosted by the same physical routers in some cases. So scaling is a key, and the way to scale today is the path towards multi-chassis systems, because in that case you can increase the capacity of a router drastically. And also another key enabler is the 100 gig support, because the capacity is going to be a key requirement here. So from technology point of view, the industry is almost ready, because already 7 years ago, it was possible with the ASIC technology to support 40 gig slot, also 10 gig line rate for a single flow was possible. And this technology was, a few years later, expanded with multi-chassis system, using actually an old cloth fabric design, which was used in telephony in the 50s. But here, from technology point of view, the success is that the switching fabric, which is internal in a router, was extracted to an external device called the matrix, using a fiber to connect multiple chassis, in order to have one single router, non-blocking routers, but with multiple chassis. So in the first version, it was with 4 chassis. In parallel, the ASIC technology has evolved. So today, it's possible to have 100 gig per slot. So the 100 gig device is ready and can be already be considered in networks. And the same model of multi-chassis is being provided by the industry in order to scale. So from scaling point of view, I don't think there is any issue with the data plane. There is a capacity to host many, many slices, virtual slices. Maybe most interesting is to look now about the control plane. Because 15 years ago, the control plane and the data plane were completely embedded together. I mean, the same CPU was doing the forwarding and doing the routing protocols, right? 10 years ago, in order to face the scaling requirement of the internet, the industry provided new systems based on the strict separation between the control plane and the forwarding plane. And the forwarding plane being done with hardware and the control plane done in software. Today, actually last year, we have started to see new capabilities that consist of decoupling completely the control plane from the data plane. So which means that you don't need to run anymore the control plane of a router inside the router, but it could be on a separate box, a dedicated hardware that is going to focus only on the control plane. That has great benefits. One is that you completely decouple from the data plane, so you can scale one component, so the data plane, for example, without touching the control plane, or vice versa. And also you benefited from technology point of view from different level of evolution, because on data plane is essentially based on ASICs, whereas the control plane is essentially based on CPU and memory evolution. But in order to benefit from this, we need to have the virtualization capability. If we can build big systems separating control plane from data plane, we need to be able to slice them. So the interest of having a separate control plane is if you share the control plane and you run multiple services in the system, as soon as you increase the number of services, you are being challenged by the processing requirement, which decrease the scaling and also the stability of the system. If you run a router with a decoupled control plane from the data plane, and if you can scale independently the control plane by having multiple routing engines, you can associate one or multiple services to a dedicated control plane system. So in terms of scaling, one service will never affect the other services. So you can continue to scale, providing more services. And what I have in mind is, of course, a virtualization slice. So you can have more virtualization sliced in the network without impacting the other. So the future POP of NRN we could imagine as a set of routers which constitute the data plane, but only the data plane, so line rate forwarding on all interfaces, including 100 gig interface. And separately from it, a dedicated hardware for just the control plane of the system. And all the chassis could be connected together with the matrix in order to constitute one single big routers, but it's a huge router that will support multiple and independent networks. And with these building blocks, then you can start to slice. So for example, you want first to build, of course, the internet network. So you create a network by taking some pieces of the data plane, so some slots or some ports from the routers, and you take one control plane board dedicated for this internet network, and you build a network. And that's typically what NRN service is today, right? Providing one network for any connectivity. That will, of course, remain. In parallel of that, you can decide to build a separate network, but you don't need anymore to deploy dedicated equipment for that. You just slice the infrastructure with another slice. And that can happen, of course, as needed according to the limitation, of course, of the hardware that support this capability. So one word on software-based implementation and hardware-based implementation, because the concept of logical router can be addressed by different ways. Today we have the possibility to support logical router software-based, so typically running a separated daemon in the control plane with a set of routing protocols independent from another daemon that will run a different set of routing protocols. So we have a strict separation, but it's at software level. The big advantage, it's there. It's very cheap because you don't need to invest in any hardware. And it provides some good separation because at control plane layer, you run separate daemons, but at data plane, you allocate some dedicated port for each daemon. So you have at data plane a strict separation, and at control plane a relative separation because you are running different daemons. However, you are sharing the same CPU, you are sharing the same kernel, right? In terms of management also, you can provide a separate access to different slices, and so a user may be able to change configuration in one slide without affecting the other. However, there is some caveats, of course, with this solution, in particular with the logging system, which logs all message from all the slides. With the hardware solution, which we call here protected system domain, which is the slides I described before, the separation is much stricter, because in that case, you have a dedicated hardware for a slice, right? The big advantage being you can run different software version on each virtualized network. A separate version, you can upgrade one version from one slide without affecting the other. So the separation is a completely new dimension. Of course, the drawback of this is it has an impact on cost because you need, of course, to dedicate some hardware, some routing engine in the rack in order to run a specific virtualization slice. But from operational point of view, you have a completely separation, and you can run two networks with two separate NOC. The third block I'm going briefly to describe is the third point is about better integration of optical and IP. And here it's an interesting topic because actually you have a long experience in that. Started with a high demanding user, but very limited number of users. You explore this light path or bandwidth on demand paradigm. And today it's interesting because we are, industry realized that SDH is coming to its end, and there are discussions to replace the SDH layer by a packet-based transport. So that provides us some interesting opportunity to enhance actually the light path paradigm with a packet-based capabilities. And why? Because we need more multiplexing in the transport layer. We need also to reduce the cost. And also the SDH paradigm was essentially point-to-point, whereas today we need to build virtualized slices that may be multi-point. So if a user wants to connect logical routers with multi-point service, packet-based transports is a way of achieving that. So I'm not going to talk more about that because I have a session tomorrow which is going to be about crisis in transport. So I'm going to talk tomorrow about that. But what is sure is that because of this change in the industry regarding the transport layer, there is a need for better integration of the router with the optical components, so with OTN interfaces, and also GMPLS to achieve a better integration at control plane layer. The OTN benefit is that you put the tunable laser in the router so you can control the lambda in the router directly, and also you beneficiate from advanced FEC algorithm which allow you to send an optical signal for very long distance, more than 1,000 kilometers. And the other benefit is that you get intelligence of the optical layer. So the router has information about the quality of the signal, and even if it has a FAC to recover from some issues, it can detect that the signal is becoming weaker and can anticipate some failure and take some measure before we get a failure. With GMPLS, this is actually augmented because you have a better integration of the optical layer and IP layer. For example, here, if you have a path established between router and optical devices, and if one node breaks in the middle in the optical path, automatically we would think about a recovery mechanism from the optical network to reconfigure the lambda through a different path. However, the lambda may not be available somewhere in the network because it's already occupied. In that case, what do you do? It's a failure, right? You cannot recover. With some GMPLS intelligence, where the optical layer could better communicate with the IP layer, with the router, we could learn about that issue, that the lambda is being used in the middle of the network, and so the router could trigger different lambdas by tuning the laser, because it's software-based, and so we change the color in the interface, and we create a path with a different color that is available in the network from end to end. Right? So this is the kind of intelligence that we can enable and that will ease the virtualization in the infrastructure. And the last point I want to mention here, which is totally different, but I think probably as important as the previous ones, is towards improving innovation. Today, when you deploy a network, you use commercial devices in most cases. You are using the software of the vendors, which provide you a set of services, which are the services that the industry needs in general, right? Sometimes we develop features specifically for a community, like the R&D community, but in most cases you use all the same software. However, we see more and more value in implementing services and applications within the network. So why not thinking about starting to develop your own application or your own service, your own protocols inside the infrastructure? That's something that is, looks a bit like science fiction, but is actually possible today. And that would improve the innovation in your network. Of course, if we start to do this, that means we may have to upgrade more and more the network, because you are going to become engineers developing some capabilities, so you may need to have more frequent upgrade of the different networks, and each slice will be upgraded independently. So we need to look after some ways of improving upgradability of the network without interrupting the services. So that's why I think here, as requirement, we have to consider as key building block SDK, software development kit, available in the router, as well as in-service software upgrade capabilities to allow you to upgrade without service interruption. And that's something that is now actually possible. It started recently, but now the industry starts to propose this kind of capabilities in routing system. This is very famous in end systems, so in the operating system of a PC or in a mobile set like the iPhone. It's something that is already available, but in the router system, this is new, and that really opened new direction. So on top of the software provided by industry, you can develop your own modules. And the way it works is that you develop a source code that you compile yourself, you sign it, so it's going to be recognized by the router as an authorized piece of code. And the code can affect either the control plane or the data plane. So you may create a new routing protocol, like BGP V5, for example, or you may decide to change some behavior in the data plane. So when you have a packet coming in and going out, you may have an intelligent treatment in the packet, like adding a tag on it, or maybe do some monitoring, or I don't know, it could be anything like deep packet inspection, encryption. We can imagine any application that affect the packets crossing the router. So application could run both at the control plane and at the data plane, and of course this way you have a better integration of application with the other network elements, because it's embedded in the infrastructure. And that's a big advantage compared to separating this application in dedicated nodes, because otherwise you would run overlay networks. And here you beneficiate from the state-of-the-art industry solution for the routers with line rate forwarding, but running your own application. So orthogonal to this, but I think important is if you start to play with this, you will have more and more frequent upgrade in your network, more than today, because you are running very stable services. But here you want to do try and error approach. You have a new application, you try it. If it works, it's a success. If it's not a success, you remove it and you change. So you need to upgrade quite frequently the systems. And for us, it's very important to provide this in-service software upgrade capability so that you can upgrade without interrupting the service. Okay, so as you have seen, I went through several building blocks that I believe are very important to be foundation. Very few are being used today in research education networks of all the things I just described here. Very few. So I think there is a real opportunity because they are available. You can deploy them in different ways. You have building blocks that allow you to explore a new paradigm that is also interested for commercial networks, but they will probably be slower in doing this than you because you have you can be much quicker. You are also already involved in some project like Federica and Manticore, which are already looking at this from a service angle, so it's not a pure research. So I think you just have now maybe as a next step start to investigate how to integrate this as a native service in your infrastructure if you think that's interesting. And the opportunity here is again to take the lead on something new and actually decouple the innovation in NRNs. Thank you very much.
So, thank you very much, Jean-Marc. Any questions to Jean-Marc? If not, I'm just wondering how many of you are from an NRAN or a campus network operator, and how many of you are interested in some level of virtualization into this network? Okay, that's
okay,
good.
Interesting. Very good.
So thanks again. Our next speaker is Radek from the Polish Supercomputing and Networking Center, PSNC. Trying to find your talk. It's not your first slide, right?
Okay, so I'm Radek Krzywania from Poznań Supercomputing and Networking Center. I made this presentation with my colleague from the same institution, Piotrowicz. He's the optical guy who helped me a lot with some issues. So the topic of the presentation is the something I called failure as a service. So simulation of the real network failures in the virtual environment, in the virtual networks. The physical and the virtual worlds are closely together. There is a lot of research doing in that area. Several projects, just mentioning Federica, Genie, or Forward project, who simulate network itself. The difference between virtualization and the network virtualization is mostly that we don't want to virtualize computing resources like server endpoints or something like that, but we are focused more on the connectivity network, network equipment, routers, switches. This is the point of what we are trying to do in those projects. So if we make a virtual environment, a virtual network for the end user, the end user has some expectations from that. Well, the first one is that the network is the perfect one. There is no troubles, no drop frames, no issues at all, and all the transfer is working perfectly, so they can validate the applications and the whatever they want to do with that network. But we think that there are still some users that want to have a view on somehow a real environment with all those failures and things that may happen into the network at the lower or higher levels that can influence the topic of the end user research, like protocols or applications or whatever they do. Also, the user wants to have access to the layers of the virtual infrastructure in which he is interested to. Also going down to layer 1, optical, electrical, or whatever. which is quite complex in virtualization environment. If you do, for example, links as the VLANs, it's very difficult to give user access to the SDH or optical layer in the physical world. That causes another problem, the possibility of debugging of that network in case of issues and failures, and also bottlenecks for tuning the network, and access, physical access to the equipment, which in particular does not exist because it's virtual one. So there are two aspects of the virtualization. The first one is the real physical network is influencing the virtual world. So any kind of failures, any kind of issues, things that may happen in the physical infrastructure is affecting the virtual one, sometimes at higher scale. So for example, if this link is going down between two physical routers, and we have in the virtual world the big failure of 5 other links that are virtualized over the single physical one. Also, if the one of the physical node is down, again, some, not one, but many of the virtual nodes may become inaccessible and will stop performing. Probably the user will try to know how to solve that issues, but having no access to the physical infrastructures make it quite impossible. For example, we have a bottleneck here. We have a physical infrastructure, 2 routers, a switch, and the optical environment at the bottom. And this link is not performing very well. The users just see that this link between 2 logical routers at the level 3, because it's the lower level he has access to, is underperforming. He can check counters or issues on the routers of layer 3, but he has no access to the physical equipment at the bottom. And for example, an issue is at this optical link. There's no way for the user of the virtual infrastructure to debug that thing and to say what is wrong with his network, because he has no access to it. And in fact, the virtual infrastructure is not working there properly, so he don't know why his application is not working. He has no idea why his protocols is not working. And he needs an extra support from the physical infrastructure administrators to solve that kind of issues. What are those issues? For example, the user can tune the endpoints of his virtual infrastructure, but he has no control over the virtualization mechanism, the virtualization system like VMware, OpenVZ, or things like that, which can underperform or limit the performance of the network, of the system, of the transmitting equipment. No access to the physical driver of the operating system, which sometimes can be tuned, can be manipulated. You can increase buffers on that, or add some TCP enhancements or whatever, which you are not allowed to do if you have just a virtual machine and you have no access to the physical driver, which is controlling the physical interface on that machine. The other things that can influence virtual infrastructure is packet drop, packet loss, jitter, high delays. Again, the same issue, no access to physical infrastructure. You cannot diagnose it, you cannot say why the things are happening and how to solve it. This is another example in the real world. Again, routers. Packet is lost at this connection. So this is the virtual infrastructure. That's the physical one. The user can check counters at both of those routers. So he can see that the packets are leaving this router. Everything seems to be fine, but they are not reaching this one. So probably this link is down, and that's the end of the debugging, because he cannot do anything more. He can say that the fiber or whatever is cut or something like that. In fact, the real reason is that the router, the physical one, can be highly utilized, and there is a congestion on that. There's insufficient buffers. And the reason for packet loss here is completely different than it was assumed at the virtual infrastructure. The problem cannot be solved at separate layers. So the question is if that was the influence of the real environment, the physical, into virtual one. I tried to reverse the problem, and that's the main topic of this presentation. Is the utopia is the objective for the network. So does really user want to have a perfect network, sending all the packets, and every packet is reaching its destination at the highest speed? If so, then why do we need transport protocols like TCP or TCP enhancement or whatever? Just use UDP, send your packets, everyone is happy, every piece of information you send is reaching its destination, the status is unchanged. So what about users who want to test failures? The response of the application of the protocol on the network failure. That may be difficult if you have this level of virtualization as you have at this moment of the research. So we need to define those users. There will be no much technical material on this presentation because we just started working on that. But we need to define those users. Who are those people? The first guess is the people that are developing the routing protocols, for example, or the application that are maybe easily influenced by network traffic conditions. I'm very open to other suggestions, so if you are interested or want to have some opinion, then at the end of the presentation I'll really open on that. So what kind of failures can occur at different level of the network? So the application layer, the highest one, the incomplete data transfer, missing information. If you send a UDP stream, some packets or frames are dropped, you don't have a complete information at the end. If you have an application that it depends strongly on the information you send, then you can check how fragile is it on the missing information. In case of the voice transmitting, for example, you will just have missing words or things like that. But there are some more restrictive applications where the delay needs to be at some level, or jitter needs to be at some level, and you can test them how they can handle various situations at this level. The transport layer is the issue with reconstructing the information that was sent. So the influence of reordering, jitter things. What can you do there is the testing, for example, of the TCP enhancement protocol, which was at least hot topic some time ago. Layer 3 is the IP network. You can drop a packet, you can have packet loss here, you can limit the transfer. You can modify the routing protocols, routing algorithms, and you can, for example, test how the behavior of the routing protocols at that level. In case of failure, for example, if you cut the link and the BGP needs to reroute some packets. And then we have the most interesting layers, the layer 2 and layer 1. Layer 2 is difficult to virtualize and provide that infrastructure to the end user, but from their perspective, it may be interesting to see how network is behaving if they have frame drop, issues with the spanning tree protocol or VLANs misconfiguration, for example. So they can validate before the deployment into the real world, they can validate the configuration of the switching equipment. And the layer 1, here's the example of the optical network, but it also can be the electrical signal over the Cooper wires. So the degradation of the signal, the influence of the optical effects in that, nonlinear or linear effects, which in fact is the changing bits at the lower layer, changing the information, so it also influences the highest level. So how to virtualize that? Application layer, transport layer, and IP layer are not very difficult, and there's already a lot of research how to do that. We just adopt those ideas into the virtual environment. So, for example, if you have the voice streaming here, and you are using UDP instead of TCP, you are fragile on some effects that may happen in the network, and you want to examine how the application at the application level is behaving if something bad is happening. So in that case, we have sending 7 packets from the sender, but only 4 of them or 3 of them is received at the end. Question is why and how the application will solve it. So to emulate that kind of a failure, as the FreeBSD DummyNet tool that is well known for all of you, I suppose. When you can increase the delay of the network, you can drop some packets, and you can simulate what is happening if the network is underperforming in that case. So you can shape the bandwidth or whatever. In that particular case, you just dropped several IP packets out of the network, and the receiver doesn't get the full bunch of information, and you can try to find what is the limit, when the application will be still behaving properly if you lose 10%, 20%, or 50% of the information. Where is the border? Yeah, so that's the dummy net example. The other thing is the layer 2 virtualization. It's a little more complex thing. It may require support from the vendors. Probably, I don't know how is the logical router, at which level you have access to the equipment, if you can have access to the layer 2, or just the IP routing mechanism. So I don't know, but without the access and support from the physical equipment, it will be difficult to virtualize layer 2 equipment. There is the tool of okay, we need to have some things are supportive to virtualize layer 2 things. One important thing is the so-called Q&Q. So for example, if you have virtual links realized as a VLANs in the physical network, and the user wants to have their own VLANs, so to use the layer 2 infrastructure, the virtual layer 2 infrastructure, without Q&Q, they will not be allowed to make their own VLANs in the network. If you have Q&Q, you can have VLANs into the VLANs. So the user may want to define their own layer 2 infrastructure based on VLANs, despite of the physical one that is provided by the network provider or administrators. And there is a tool that may be helpful for creating the layer 2 switches on the end boxes, on the endpoints. This is a standard Linux bridge tool. It's an open source project, so you can modify that code and play a lot with that, trying to emulate as much feature as possible in the Ethernet network. So what can you do in the layer 2, in fact? So one of the ideas, there's 3 of them, is to try to make a loops in the virtual infrastructure. To check the spanning tree protocol or some other alternatives to that, or find always an own solution for solving that kind of issues. You can also simulate the hardware failures at some point by modification of our IRP tables or putting up and down interfaces of in fact, a Linux box, but it will behave as a real layer 2 switch. If we have access to the more advanced infrastructure, like, I don't know, in Juniper, for example, maybe we will have possibility to play with MPLS or other layer 2 technologies. But the bridging tool on the Linux is just a simple things like the office switches. It doesn't perform much of the business class or supercomputing class switches. That's the limitation for the layer 2. The main, another way of the layer 2 issues are frame drops and the modification of the checksum at the end, which in fact cause frame drops as the result. What we need for that, to do that thing, is to modify the network interface driver, the piece of a code that is controlling the network card, to just drop a frame at just every second or every 10th or every 100th frame going out of the machine can be just dropped. And also I already find a piece of code on the internet that is allowing sending and receiving the frames with CRC, with the checksum, wrong checksum. So you can send packet which was modified in the network at some point. We can use that features for simulation failures at the layer 2 that influences all the layers in higher. So frame drop is in fact it will result in dropping the IP packet. You can simulate the congestion of the switch because if the buffers are full, then you just drop the packets that you cannot handle anymore. And also, what is very important for me is that the frame drop can simulate the lower layer failures. So if the optical layer is changing 1 bit in the frame, the checksum is wrong, so the frame is dropped. And now we come to the virtualization of the layer 1. So I will focus on the optical thing because they were more interesting for me. In the next slide, I will tell you why frame drop is so important for me here. So virtualization of the layer 1 may be quite resource consuming because it's done by the hardware. So if you try to virtualize in the software, trying to analyze every bit of information in the frames and packets, it will take a lot of time and will decrease the transfer, the performing of the particular virtual machine or whole the physical machine as a whole. They are competing for the resources, not only network interfaces, but also CPU for calculations or hard disk drive for storing some information. So you don't have the full performance of the physical machine, and also you don't have the full performance because you are doing that manually, let's say, which means the software. There's no software support for that. So virtualizing the layer 1 issues by analyzing bit one by one, it's too time consuming for the virtualization. For example, if you have a single network interface, 1 gig interface with 4 virtual machines, if you use the fairly shared policy, then you have 250 megs per each virtual machine or operating system. So that visualizes the issue we have here. And because of that, we need to find a way how to virtualize the lower level effects in the higher network. And the good thing is that if we change a single bit of information, if the optical layer is not able to correct it, so you just build a frame, an Ethernet frame out of that bits, and you validate the checksum at the end, and the checksum is different because the information was changed, you just drop a frame, and it's much faster than investigating all the bits separately in the network. So in anything is missing or changed in the lower level, the optical level, you can show it to the higher levels, layer 2, at that point, as a frame drop. You just drop a piece of information. Here we have the example of the Ethernet frame, a very simple one. The probability of change is mostly in the data area because this is the longest part of that frame. But anyway, whatever you change on information, either in the preamble or frame header or data or CRC, the whole frame is dropped anyway, and that's the policy of the internet. Unless you have some correction algorithms at the optical level to handle some level of the failures. But in general, the frame is dropped, and you missed that part of information. Yeah, that's the CRC is calculated from all the information of the frame. Okay, so to debug a layer 1 issue, you need to have very expensive equipment for validating the fibers to see how they behave, how the light behaves in that fibers, how it's degraded, to measure the optical effects in that network. And you also need to have a physical access to those fibers. The part of that, the whole fibers, the whole link between their distance in the with the nodes in the middle. So there's a various way of measurements. Sometimes it's enough to have just access to one point. Sometimes you need to have it at both ends of the fiber. But anyway, you need to travel to some places. You need to have expensive equipment which you need to transport in various locations, and that's from the economical point of view, it's quite expensive. So that's why I think it's the virtualization may be helpful here for learning, for example. Also, the background of the virtualization, the physical network, may not be the optical one. So you virtualize network, the optical network on the Ethernet network by saying a VLAN is an optical link. So, and the user wants to have a virtualization of the optical link. So he wants to have optical effects on the link at the very low level. Well, this infrastructure does not exist physically. So again, you need to emulate those kind of links at the lower level. Yeah, this is an example of that. You have gigabit Ethernet switches and one VLAN created between endpoints, but the user wants to have this thing as an optical link and want to have the measurements over that. So I think this is the older version of the PowerPoint here, so that's why it's slightly changed. But anyway, the main idea of that is to put at the level of operating system or network interface, we need to investigate that the attributes of the optical connection, so the attenuation, the power of the lasers at both ends, the length of this of the fiber, the information about dispersion, both chromatic and polarization mode dispersion, and provide users with the virtual measurement tools, a piece of software that, based on the attributes, can calculate how the real graphs for that fibers can look like. So he doesn't need to have a very expensive equipment, just a bunch of software to see how, with high probability, the results of the measurement will look like. The origin of that is, as I said, changing a single bit of the information. So there is no ideal world, and this is the analog world, in fact, at the optical level. And we have the effects that are not known for the Ethernet networks, for example, when you have just bits of the information in the frame and you can read it. Here you can have some effects that just shift some bytes in forward. You have some tolerations for solving that, but in some cases you are unable to correct those errors and you just lose single bits of information. We have a very interesting thing is chromatic dispersion in that case, for example. When you extend the bit of information to the length of that, it was, as it sent was very short, and then it's extending, and at the end the single bit of information is longer and the device needs to process it correctly. The similar thing is for polarization mode dispersion, where the signal is spreading in a different polarization mode. This is the better example of that in the fiber, when you are sending a single impulse to the network, and at the end on the vertical axis the signal is traveling a little faster, the light pulse, but on the horizontal is a little slower. So in fact the impulse of the light is longer than at the beginning. And if you send two pulses of light, they can overlap each other. And if that was 1, 0, 1, at the end it's 1, 1, 1. And that's the issue on the optical networks we want to emulate and investigate how it behaves. So the polarization mode dispersion is a quite difficult problem to solve, because it depends on some, not on the attributes of the fiber itself, but mostly on the physical things that became in the fiber, how it looks like, the geometry of the optical fiber, the pressure, how it looks like, how it's connected. If it's banded, also the temperature have influence on that, so it's quite difficult to predict the value of that. But that's why it's so interesting to investigate. The comparison of the most interesting effects of chromatic and polarization dispersion looks like that. So the chromatic is linear. If you have all the attributes of the fiber, you can calculate the you have a mathematical model to see how the signal will look at the end of the fiber, how it will be received. It's already done, in fact. There are mathematical models for that, not very complicated. So it's easy thing to modulate in virtual networks. But polarization mode dispersion is a completely different thing. It's somehow a stochastic process. It's random. You cannot predict it. The only thing you can do is to measure it at the end when the link is set up. And in case of failure, you can measure it again to see if it changed at some point, influencing the transfer in the links. So maybe this is the better way for virtualization of that. At the end, I want to show you the short example of the network debugging. So the idea that is behind all those failure as a service idea. So let's assume we have this kind of a topology. This is the virtual topology with 1 gig link, 3 routers, 1 switch, 2 endpoints. The link is underperforming, having only 100 megabits of transfer, and we want to investigate why does it happen. So we do ping. The first thing we can do is to do the ping, and we have 10% packet loss, which is quite high for this kind of link. So we try to, another step is to define where the packets are lost in this network. So we are trying to do the trace route to the endpoint, and we discovered that the packets are lost at this link between the second and the third router. To investigate that issue in more details, we need to go to the lower level, so the layer 2. So we have a layer 2 virtualized here, so we have a switch. We can compare the counters of outgoing information from the router and incoming to the switch. At this case, we can see frame drop. So the packets, the frames, are missing somewhere at that link, because the router, the switch does not see them, and they need to disappear somewhere at the link. The reason for that is because we modified the network interface driver, having those attributes information to change the checksum information in the frames and invalidating them at the end. So the switch, after receiving those information, will just do the frame drop. But the switch software itself will not be aware of that, so it will just show it on the counters that there's a failure rate at some level, and there is the last packet received that was sent from the router. Oops. Okay, so we know that there is something wrong with the link, the physical link, and the information on that link is changed at some level. So the same information that was defined to calculate the probability of the bit change and the probability of the frame drop at the same time is used to generate the view on the virtual measurement equipment, the optical network analyzer. And at that point, the user can have the view how the physical link, the physical optical link may look like at this moment. And he can decide, for example, and find out that the polarization mode dispersion is much higher than it was initially at the beginning when we set up this connection. The reason for that may be different. The temperature has changed, someone has bended the fiber, or it's broken somewhere, or whatever. But he gets to the layer 1 information, what can be wrong. So why? This is the attributes that can be used for just not all of them, but the example of the attributes that can be used for the mathematical model to simulate those optical issues. Why to do that? The idea is, as you can see on the slides, the first thing is to validate the network before deployment. So you can build the down from layer 1 to layer 7 the network environment and see how it will behave, and if you are satisfied with the performance or the quality of the connections. You can also try to tune or find out what physical or hardware attributes you should use in the network to have a good connectivity. For example, what is the strength of the laser, the power of the laser to be installed on the 100 kilometers link, or do you need some amplifiers in the middle or not, and what kind of amplifiers, how the dispersion will influence the signal, and how to change them, how to correct it with the proper tools. The another important thing is for the educational purposes. So you can try network people how to debug network issues and what can cause the network failures in the physical environment without having access to the expensive environment. The same is also for student, for educational. You don't need to buy a very expensive equipment, several boxes, each measuring different optical attributes, and sending them 100 kilometers around the country just to learn them how to measure those attributes. You can have everything in one lab, on a couple of servers or network equipment, providing them a very light environment, a very cheap one, to learn them how to debug the network and how to solve the network issues in the real environment. So the main idea is economy, of course, as usual in virtualization. And some failures in the network are very rare and may not occur very often, but just from time to time. And if you want to train people to find out those issues and solve them, you need to have a way to either make that failure possible in the physical environment, which may sometimes be quite difficult, or you have a failure on demand, failure as a service. So you can create that failure and learn end users how to solve it. So that's the idea behind of that. Okay, thank you from my side, that's all.
Any questions? No questions? One question there, Jean-Marc.
Do you think there would be some interest of having such simulated failure service embedded in the infrastructure, such as today you show the path from one node to another, crossing different switches and then routers, but instead of having this failure generated by a separate node in the middle, would it make sense to have it as a software component inside the infrastructure?
So So you have a physical infrastructure,
Yeah.
you just put a box.
So if you take a router or a switch, would it make sense to have part of this system, which is a system provided by industry?
So instead of introducing that to the virtual environment, you introduce the failures to the physical one.
But could be done at the virtual slice level, of course,
Yes,
at the virtual slice level. But instead of having a separate component, could it be a service provided by the infrastructure inside the systems? Like
It's possible.
Yeah.
It's not closed environment. You can modify this idea.
Yeah, just want to make a parallel with my presentation where I talked about possibly of developing your own applications running on routers, for example.
Yeah,
If that could be one.
Yeah.
I mean,
It can be very useful.
one potential.
Case, yeah.
Okay, thanks.
So thank you very much. Thank you, Radek. So actually the main message for me was that if you virtualize your network, then you obviously virtualize its failures as well. So then you need some proper tools to detect and then to debug those failures. So our next speaker will speak about the monitoring solutions in a virtual environment. And he is Jürgen Avratel from Cessnet.
Good morning or afternoon, I don't know, so it depends how you split the day. If 12 o'clock is the just end of the morning, but sometimes the people splitting in by lunch, okay. So I will talk about why we need the new forms of the monitoring in the overlay networks. Seems me that I will, you can see the Federica, so I will talk about the Federica project more or less. And in the beginning I said that we should repeat what was the main goal of the Federica. So we try to create a playground for the network engineers or other scientists who need experimental networks for testing new ideas, proofs, new concepts, and so on for future internet, okay? And of course the main feature of this network should be that each group of the users should play in the Federica independently, fully separated from other players. Okay, so this is the one of the main feature of Federica. And because I will talk about some results which we achieved in the current status of Federica, I have to also explain a little bit, this is a danger here, what Federica is, because, and I should explain in 5 or 10 minutes only. Okay, so it's quite difficult, quite difficult task. So you will see the Federica topology, which is separated in 2 groups. The one is called the core groups, the other is the non-core groups. Okay, the core group is between the Poland, Germany, Italy, and Czech, and the rest is like this. But this is nothing special. I just want to say that Federica is not multi-domain network, okay? So people like to talk about the multi-domain monitoring, multi-domain provisioning, and so on. This is the Federica.eu. This is the one domain, and every sites are under control of one person, which is sitting over there, so maybe the NOC. And even if the devices and the nodes are located in different countries, so it's the one private network, which is the similar like IBM Com or HPM Com or Cisco or Juniper Com and so on. Okay, so even if they have access to all these networks, they have access into the internet because they need the users. So. When I entered the Federica project, so I had a dream that the Federica with the virtualization can be overlaid. And so finally we can have the more Federica's levels. Okay, so we can have each level which would be the instance of the same Federica. And so it's for the users, what I've said. Some type of users can use it like in Winnie project, they have the internet in the slice. So we can have internet in the slice in the first slice. Then in the second, we can have a second internet in the slice according the imagination of another designer. And in third, we can have the application which is for IP telephony, in third voice over IP, video over IP, and so on. So we can have a different type of application inside Federica. How we can achieve this, the final solution? So we have a typical site configuration. Doesn't matter if it's core and non-core. So we have there some switches or routers, and we have the node machines which we can use for these as a resources, as a virtual entities on the level of the computing, and the virtual entities on the level of the network. So this is our building elements for the Federica. So if you will see the physical infrastructure, very simple case. So you can see that the NRAN, the users are sitting in NRAN on one side, on the other side, and there is a Federica physical nodes and physical links which are built on the giant links. Okay. So what we can do is in the first step we can multiply the nodes. So we are using the VMware to multiply the nodes. So we create the virtual nodes, and after that we put them into the some slices which are created according to the wish of the users. And of course, if we want to create this complex structure which I showed a few minutes ago, so we have to have the connection between these virtual nodes. And I like this type of the presentation when you can see the multiplication of the physical nodes in the vertical. Okay, and the links are built via the special tools. We have heard here about the Manticore, and we have heard here about the virtual routers and so on. So, but users, they will not see it. Okay, if we are building the virtual, all these lines which are in the slices are virtual passes, and they are built based on these routers and switches which are used in the configuration each host. Okay, but for the users we offer just the virtual entities in the computer resources, and they can do what they want with this. So if they use this computer as a source of the application, or they can convert it into the virtual router or virtual switch or virtual whatever, and they can create own network inside this. So we give them really independent environment, and it depends on the user how he will use it. So if we finally go into the monitoring, so we have a physical infrastructure, and we have to monitor a physical infrastructure like other networks are monitored. Okay. So after that, we have something which I call which is how this physical machine, this sun machine, which we are using the sun machine, is used by different slices. And after that, we have the level of the slice. That means the user level, and we have to monitor how user level of these networks behaves. So we have something which is the physical centric and the node centric or slice centric information. Okay, so and if we go into the physical levels. So we have a map which shows, for example, the core nodes and all interfaces which are going there. And you can see the scale which shows the traffic which goes from A to B or yeah, I updated this, okay. But it's a very stable machine.
Yeah, it's reliable enough. So
yeah.
That was the test. Let's go ahead, I can do
it's happened to me twice, so
I can do that, just go ahead.
Okay, okay. So you can see the scale, which shows that the traffic between the Poznań and Milano is the light blue. That means in this level and so. And frankly said, you can.
No, it's okay. That was me. Sorry.
Okay, and you can roughly see that from VMNIC from Erlangen goes traffic to Prague. Like via this. So this is just orientation map which gives you the general view what is going on. Okay, and if you click on any of the points, you will get some classical statistics which shows the last 24 hours or last week or last month in the I/O and so on. So you can see it's nothing different. So you can use the MRTG, you can cricket or what you want. So it gives you the classical. So physical infrastructure again. So this is our interpretation of the set of the IP addresses which are used inside the Federica. And again, if you click on this, if it's green, so it's running, and if it's red, it's not running. So you click on it, and you will get the graphs with the statistics. Okay. And of course, it's create also the trouble tickets which goes to the NOC and tell them that it's the color change from the green to red. We can use also the Nagios for that monitoring, but it doesn't give you anything else than what I showed you before. So we are still on the physical level of this. If I go into the practical slicing, so the users are coming with the different requests. So I use the cases when there is created a star network between AD, AC, AB, or the circle network AD, BCD, A, and it's created via VLAN. So we have heard here in the previous section that the VLANs are somehow doing the communication. So in the Federica core, and these VLANs are created on these devices, networking devices. And if you go a little bit farther into the techniques, so again, you can see that there is some Ethernet switch or MX or EX. It depends, it's the core or not core. And after that, you have the vNode, which is the ESXi server, on which you can create these virtual machines, and in virtual machines you are running the different slices. And because it depends, if we are using Q-in-Q, again, it was mentioned here, it depends where we will tagging and untagging the Q-in-Q, okay? It depends if we will do it on this edge, and we will go with the particular VLANs into the slices, or if we will do it inside the vNode. So, and there are two limitations. So, of course, this limit gives the number only on a number of VMNIC which we have on each node, but this solution has practically no limit. So it's done by the VMware variability. So it's very flexible and very wide, but also the other systems give you such type of the possibility to create virtual switches inside the infrastructure, and after that you can use the queuing queue in a very variable form and get a lot of VLANs. So this is again the picture which and the case which I show you, that the slices appear and disappear because we are saying that in Federica we are working on demand of the users. So if the users want the slice, okay, we will create a slice for him, but after a week the slice disappear, or after months slice disappear, and the other slices are generated. Okay, so it's a very dynamic process. So you can see that in any vNode we can have many virtual machine and many slices, and on each vNode it can be different because not all users will use the all nodes. So this is the simplest case of the slice which we use just for testing of our monitoring system. So we have a slice which is from three points, the Erlangen, Milano, and Prague, and so you can get it from internet via so-called access point which is in Poznań, and via management network you can download what you want into these virtual nodes, and after that everything is running, okay? And you can see which the private network which was created for this VLAN which was created for this private network or the slice, okay? So, and of course I will skip this. So VMware offer some monitoring tools for the managers of the nodes, but it cannot be used for the users in the Federica, which are from different countries, and so you cannot give them the rights to access each nodes, because on each node is running more slices and more applications, okay? So I just want to show you that there are some tools which can be used, but generally, but not for our project, okay? So I will just skip it. So our new tools which we developed more or less according the hint from the Planet Lab, which are doing the similar way. So we have the list of nodes, and we have some critical parameters which we show on the web, and you can see that there is a CPU capacity which is used, and you can see also the network usage in kilobits per second, okay? And so again, if you click on the particle side, you will get the more information. You will get the names of the virtual machine, how many CPU in the megahertz are using, and you will get some statistic during about the CPU or about the traffic on this node. Of course, you can get much more information about more details about MAC addresses and the other things. Okay. So, but what's important, you also get the VLAN ID, 203, 201, 2000, and so on. And it's important to know that the user in the slice can get this information. Slice-centric mode is quite difficult, and we still need more work on it, and we need the configuration data from central database, because if the things are generated dynamically, so you have to have not only the mail or something like that, which gives you the information what's going on, but you have to really have a database in which you will store the details about the creation, new virtual resources inside the Federica. And we need a more detailed coordination with NOC, because the NOC is responsible for a very important part, the creation of the slice. And we need automated links between the all admin tools, and we still are working on it. Anyway, I would like to show you a few other examples or the experiments which we did on the micro slice, okay? And we just use it for testing our monitoring tools, that we are able to detect some traffic, okay? So first of all, I was talking about the Snmp V3 Monitor. It was the first picture which I showed. So I must say that we selected the cheapest or free of charge the version of VMware. And this VMware doesn't support fully Snmp. So we cannot get the Snmp data as I/O directly from the machine. So we have to use the proprietary tool which is available inside VMware. And so the first graph and third graph is from this proprietary tool. And you can see VMNIC and which VMNIC is used. So on this picture, the only VMNIC 2 is used. But we are doing the Snmp monitoring on the edge of the routers, or on the edge on the switches. So we can compare what we are getting from the real VMware and from which VMNIC, and we can compare it with what we get from the Snmp monitor. So this example I called the correlation CPU load versus network. So it was one question about that Sunday afternoon when we had a session here. So you can see the two types of application. The one is the trivial application, SCP 4 giga file from one side to another side. It generates such much traffic. But if you compare it with the CPU core, so you can see that from 2%, it grows into the 10%, okay? But after that, you have another type of application where you are doing some type of processing. So, and if you are looking on the load of the CPU, so the percentage is a little bit higher, but still, this is resource sharing. We have the 8 CPUs on every node. So we have 160,000 units available, and practically just very small fraction of it is used. And also the sharing of the CPU and CPU distribution on host on the load is very random, because it's the Snmp, and after that there is another rules which are inside a virtual machine or in the hypervisor of the VMware. So you can see that even if you are running something, it's fluctuating between CPU 0 and CPU 7 in this way. Okay. So, so this is the multi-line. So every CPU has its own curve, and this is the stack. That means we stacked the load for the particle scan, and the red line gives the sum of the CPU used. So, and if you look on this CPU sharing a little bit in detail, you can see that, for example, on the node is running 5 virtual machines. Of course, the one dominate, and 4 CPUs are active, and but CPU activity is 0.13% only, okay? And in this case, even less, 7 virtual machine, 9 virtual machine, and the 0.14%. That means we still have enough capacity to create many slices on the hosts. Okay, so and if I use again some type of stack, and if in positive way, is in positive direction, I use the utilization of CPU, and in negative way, I am using the idle time when the machines are running practically nothing. So you can see that the big difference. Okay, so and this is the reality in the individual graphs. This is the, compared to Planet Lab, they have a similar statistics. And for example, they are running 73 slices on the one side. And they still have, and they have usually one or maximally two CPUs. So, and if you look on the CPUs, the distribution, so again there is one slice which usually dominate, and the other is the exponential down type of curve. So the conclusion is that most slices are running randomly. Some is just created but not running at all, and so it allows the stronger over allocation of the processes. And finally, I would talk just 1 minute about the external probe monitoring, which is quite important, and the reason is what was said in the two previous talks. Because even if we have the count of I/O, we don't know where these data are coming, if from which, because normally in the internet you have a trace route, but if you start to use the VLAN, so this trace route doesn't work because everything is masked, everything is hidden, so you really don't know from which side you go, from which side the packets go, where go. So we are using the flow mount probe in one of our sites. We are monitoring all inputs and outputs, and so after that we can get such type of information, which is the information from which direction the flows are coming, and after that you can get some type of the information about the VLAN, how they behave, the VLANs, and you can separate it again on the TCP, UDP, ICMP, and other, and still you have the information from which direction it comes and where the packets are coming. So the final, this picture which we have over here, well, sorry. So this one can be more detail if we really will know that these packets which are from here are coming via this line to Poznań and ending in the Ethernet 2. Okay, this is just the graphical, and it can be recognized only in the case where there is no traffic. And only one traffic, which I generate as a test traffic, goes from here to here. But if there is a real shared traffic, so you cannot see anything, you have to have some monitor which gives you the information, okay, so this is going from VMNIC 1, which belongs to slice 1, and it go to Poznań, which also belong to slice 1, okay. So this is important, and I just want to say that we have another talk, Jiří Novotný, who will talk about this, and there is a poster which explains the situation, how we want to monitor this direction, or the recognizing the slices in the network, and some type of the new type of trace routing, okay, in the VLAN. So, and I think this is all what I want to say, and if I was a little bit in time press. Okay, so.
Final question before lunch? If no question, you can go for lunch. Thank you very much.